So today I'm going to tell you about some work I've been doing at Optiver on what I call finding needles in a growing haystack and how we do intelligent reporting at scale on time series. So I work at Optiver, and we have been around for about 30 years. So it's a local company here in Amsterdam, but we also have offices in Sydney, in Chicago, and Shanghai. And we're continuing to expand as we go into new markets and look at where the opportunities are. And what we do is something called market making. And I always get a lot of people don't really understand what this is, so I thought I'd take a minute to explain what exactly this is. So a market maker or liquidity provider shows a bid and an offer in an order book. So on the, let's see if this works. Well, I'll just say. So on the right side here, I have an order book. So you have some buyers, you have some sellers, they have prices they're willing to do trades for, and there's different amounts they're willing to try to buy or sell. So what we do is we always offer both a bid and an offer price. And what we try to do is we try to narrow this gap between the highest price that buyers are willing to buy for and the lowest price that sellers are willing to sell for in order to help people make trades. Because if we're not there, then people have to actually pay a lot more to buy than they want or sell for a lot lower price than what they really want to. So we don't try to bet that the market goes up or down. Instead, we simply try to provide a price and help people actually make these transactions. And every time this transaction happens, we make this price between the bid and the ask, the spread. So that's what we do. And back in the days, this involved standing in a giant pit full of people, trying to yell the loudest of your voice to get people to hear your price. But nowadays, this is really an IT job. So we have co-located servers around the world, and working as a trader means staring at 6 gigantic computer screens full of information trying to make decisions. So we collect a lot of data. So one of the markets we're active in is Eurex in Frankfurt. And on a single day last year, we recorded 180 gigabytes of network traffic. We made 100 gigabytes of log files. And in just a single hour at the end of the day, there were 20,000 changes on a stock, the Deutsche Bank. On the futures, there's twice as much, over 40,000. And if you look at the options, which is what we trade most actively, there were more than 2.3 million changes. So we generate tons of data across the day because we're trading on multiple markets around the world. And the problem, like many of you face, is that this data is growing over time. So on this chart, I have the number of orders we're sending per day and a measure of how fast the exchange is in orange. So what you can see is that as time goes on, the exchanges are getting faster and faster, and as a result, we're doing more and more transactions with the exchange. But the problem is, as a market maker, we need to try to make sure our prices are always up to date and that we're making the trades we want. So we need to constantly try to monitor, are we doing a good job or not? So I'm on the data team at Optiver, and what we do is we handle this whole pipeline. So we collect data in the colocation, we move it to Amsterdam for our data warehousing, and then we do a lot of work trying to select and enrich the data, and then in the end serve analysis and reports to people throughout the company. So one of the key problems we often face is trying to basically find needles in a haystack. So this I'm showing here is a specific case in which we were making changes that we knew about that we hoped would make our trading better. So in this case, better means a lower number on this graph. And you can see as time goes on that there are a couple periods where there's a drop. So that's good, and we were trying to do this. But the problem is we trade a lot of things, and we don't have enough people really to always try to figure out, to be actively looking at these things and finding when unexpected things happen. And you might think, okay, well, I know the most important things I care about so I can track that. But the problem is that as you dig into the data deeper and deeper, there are exponentially growing numbers of time series that you might want to take a look at. So these are real numbers here going over, I think I picked like 7 different factors. So in the end, we have something like 100,000 time series that we potentially want to track every single day. So what we really need is some smart, automated way to look for interesting results. And in this talk today, I'm going to try to show you 2 different sides of how we solve this problem. So on the one hand, we need to do smart analytical work. So I'm going to try to convince you of a particular analytical philosophy and show you some statistical algorithms that we use for solving this problem. But what I often find missing in some of these talks is that it's not only having some awesome model that you're using to look at your data, there's also a lot of technical work to make it really work in production. Because again, this is stuff that we have happening live every single day, and we need this information. So I'm going to show you a little bit about some of the software architectural decisions we made in implementing our analysis, as well as the operational procedures we use for making sure this is running and we can keep track of our results. And while I'm not going to actually show you much real Python code on my slides today, our team at least, we're basically building all of the software in Python, custom software, built on top of these community projects that you hear about at PyData here today, as well as published research. So for the first part, let's take a look. I'm going to try to convince you that we can solve this analytical problem by doing automated discovery with iterative Bayesian algorithms. So as Vincent mentioned, I used to be a research scientist, and actually I never used any Bayesian statistics in my scientific research. But when I came to working in the real world at a financial company, what I found very quickly is that the benefits of Bayesian statistics really start to win out. So what challenges do we face in trying to do this analysis? Well, I think there's three different main categories. So one is that we want our analysis to be robust. So although we start with a large amount of data, as we dig deeper and deeper into our analysis, we're going to very quickly run into limits where we don't have so much data. And ideally, we'd like to have the same tools that we can apply to both these large data scales as well as small data. On the other hand, we want to stay sensitive. So we have a lot of different reports we want to look at. I told you we have up to 100,000 things we're trying to look at in this case. And I don't want to be generating lots of false positives so that people stop paying attention to the things I'm trying to find. And finally, we need to make sure we maintain performance. So again, this data is streaming in every day. And so we want to make sure that all the analysis we can do on manageable chunks of data. We don't want to have to try to load up lots of historical data every time we want to generate a report. So I think Bayesian statistics are a real key to trying to solve this problem. And at its core, Bayesian statistics can be described by this question. What can I say about my model, given my expectations, and what I see now? So in Bayesian terms, this part, what I see now, is our data that we are collecting. And before we see the data, we have some expectations. That's called the prior. And then the combination of those two things and our model then lets us have something we can say, a posterior. So in math terms, it's expressed as this simple equation here. So our posterior is equal to our likelihood times our prior. And if you're used to frequentist statistics, it's a bit of a change in perspective. So from the frequentist side of things, the parameters of your model are fixed, and you have some data which you think is a random sample of an overall population. And what you're trying to do is try to see if your two populations are the same or not. So there's a very funny comic from XKCD, something I read very regularly, where they ask, did the sun just explode? So they have a detector which lies to you 1 out of 36 times, and you get a measurement which says yes. So 1 out of 36 is less, this one observation is less than the 1 out of 36, so by a simple p-value test, you end up saying, yes, the sun exploded, but the Bayesian says, no, I don't think so. And the reason why is that as a Bayesian, your data is fixed, and instead what you're trying to say is, what is the range of possible values that my parameters could have? And as you get more data, you can make more and more clear statements about your parameters of your model. So what makes this key to solving this problem of doing analysis on growing large data sets is that we can do this in an iterative way. So again, we start with our prior belief. We collect some data. We can then compute how likely that data is given our prior. And that lets us update our posterior. But we can then use that posterior as our new prior for the next round of data we get. So let's look at an example of something real that we do. So one thing we care a lot about is the success rate of our orders. So if we're sending orders into the exchange, are we actually making the trades we want. You can think also, I heard a lot about conversion rates earlier for the Bayesian A/B testing. It's a very similar sort of thing. So we start with a prior, in this case, that we have some particular success rate. So we express it as a fraction between 0 and 1. That naturally falls as a beta distribution, if you think it is Bayesian. But we have two choices here. So we could start with an uninformative prior, which means that we think we don't really know anything about what that rate might be. But on the other hand, we could also have some stronger belief. So for example, we could take like a historical average and use that as our input. So I have a graph here showing some example probability distributions. So on the x-axis is the success rate, and on the y-axis is our probability, or likelihood in this case. So for the uninformative prior, there's all ranges of success rates have some considerable probability of being real. But in dark blue, I have the historical average one. So you can see that's much more narrow around some fixed value. But now what happens is that we collect some data, which in this case are successes or failures, so a binary outcome. And we can now compute a likelihood. In this case, it's a Bernoulli distribution because we have basically coin flips. And from that, we can update our posterior. So I've shown on the graph here that these are all beta distributions in this case. And this is what we believe the success rate is now that we've seen data. So the case in light gray is what you would do if you had this uninformative prior where beforehand we didn't know anything. So you see now it's clustering around the real value, which I think in this case was something like 40%, but I don't remember what number I put in now. But on the other hand, if we had started with this historical average, which is the dark blue, then you see the light blue curve is the posterior we get in this case. So it shifted a bit to the right because the value is not quite the same as it was before, but we're more confident in the result because we started off beforehand thinking it was somewhere close to that. So one of the key things shown here is that this updating of a posterior, because we have both a beta distribution in the beginning and in the end, has a very simple mathematical equation. So we're just keeping track of some sums of how many times we fail and how many times we succeed. And this is an example of what's called a conjugate prior. So these are analytical equations for simple models. And they're really nice because they're an equation. They're very fast. We don't need to do any optimization. We don't need to try changing all the parameters. But it's still useful, even though it's a simple model. So the graph here is some actual data that I'm monitoring. So I'm doing this sort of using a historical prior and then checking the data we get every day. And you can see we can now track how this success rate is evolving in time. And because we're doing this from a Bayesian perspective, we also have very clear ideas of uncertainty in our data. So the shading here represents a 95% credible interval. So we think with 95% probability that the real success rate is somewhere in that range. So if we have very little data, then this might get much larger. And if we have a lot of data, we'll get more and more specific about what we think that the success rate is. But we can also do more advanced things. So I recently started to learn about Bayesian non-parametric methods, and I've now become a very huge fan of them. I'm trying to figure out all the ways I can apply them to my data. So these are tools for scaling model complexity as our data size grows. So if we have little data, then we just use a simple model. We don't want to have too many parameters describing our small data set. But if we have lots of data, then we can incorporate the complexity we see in our data and use that in our model. And there are two classes of models that are used for this purpose. So the first is a Dirichlet process. So this lets you model arbitrarily complex distributions. And the other are Gaussian processes, which let you model arbitrarily complex relationships between variables, or in other words, functions. So as an example of how I'm using this, one thing I've done with this is to do sort of a regularized quantile estimation. So if you use the Dirichlet process, it also works as a conjugate prior. So you can start off with something like a parametric distribution, like a normal distribution or a log normal. And in this case, the model says that your data are just some discrete samples from this distribution. And then the posterior is an updated form of the distribution, just adding in point samples. So if you have lots and lots of data, then what happens is that you essentially just use your empirical distribution. But if you have very little data, then this prior you put in serves as sort of a regularization, making the distribution more smooth and also potentially providing some bias. But again, there are nice analytical solutions. So you're not going to be able to really read this equation probably, but this comes from a 1973 paper. And in the end, you can just compute for any particular quantile of your data some likelihood of it being a particular value. So we can use this now to get actual uncertainty estimates and again to provide some smoothing if we don't have very much data for a particular case. So to show you that this works in practice, here again are some charts showing some measurements over time for different quantiles, going in increasing colors of blue. And again, you can see that the more extreme quantiles are, of course, as you might expect, a little bit more noisy. And now we can really clearly see that there's a much larger range of data that could be, a larger range of quantiles that could be explained by this data. But again, one of the important things I wanted to show is that we can also try to figure out what events are actually interesting in our data. So to do this, I'm also using a Bayesian model. In this case, I'm doing an online linear regression to model continuously changing trend and noise in our data. And outliers are modeled as having an unusually high variance term. And again, because we're doing a Bayesian model, we have probability distributions for all the parameters of the model. So essentially, it's like a normal linear regression. The only difference is that the variance term, so this first equation here, the y is a normal distribution with some coefficients based on your data, and you have the sigma squared term. It's now divided by a weighting term. So outliers essentially are seen as having very small weight in this regression that you're doing over time. And we can model how the probability distribution of points being outliers. So we found this works quite well in practice for our data. So I have a case here which is actually just showing the trend detection part. But again, if we look at this case I showed earlier where we're doing this optimization over time, I now have in red the prediction of this online linear regression. And again, it's looking automatically to say certain points are outliers or not, and also detecting a trend. So we use this for labeling our data as being increasing or decreasing or outliers. And I'll show you later some examples of how it actually works in detecting these cases. So to recap the analysis part of things, I'll try to argue to you that Bayesian statistics are useful because they have good scaling properties. So we can go from small data sets to large data sets with the same techniques. They give us a really clear picture of how uncertain we are about our statements. And we can do it in this sort of iterative way where we process smaller chunks of data at a time. Wherever possible, we try to use conjugate priors because even though they're simple models, they're fast, so we can do them for lots of different cases. And I showed you a couple examples how we use this to calculate metrics and infer outliers and trends in our data. But again, this analysis can be nice on paper, but actually putting it into production is a lot of work. So for the second part, I'm going to tell you about how we actually scale this analysis to work in our production environment. So again, we face some different challenges. So one of the first ones is that we're collecting a lot of data every single day, and we have a lot of historical data. So we need to make sure that we don't overload our database, that we don't run out of memory on the server we're running this on. We also potentially have a very large workload. So we have a lot of different jobs we want to run, and if we're not careful, they might be too slow. Because again, we need to get the results as soon as possible, and we definitely can't have them taking more than a day. And finally, we want to make sure that our analysis is stable. So we want to check every day, are we having errors happening? Is our performance getting better, getting worse? So for the first part, I'm going to tell you about the software architecture we use to solve these problems, and then I'll show you some of the operational things we do to make sure our systems run well. So I'm going to build up the parts of the architecture in a couple pieces. So first, let's look at how we get the data. So what we tend to do, at least in our team, is that we abstract our databases with REST APIs. And these are usually Flask applications serving data. This lets us cache queries that we're getting. So if we run the same query multiple times, we already have the data downloaded. And in the program I do for this analysis reporting, we then cache larger chunks of data. So typically for the data for an entire day, for some trading environment or trading market. And then each report is for some subset of this data. So what we can do is then with this cached data, we can use simple filtering, aggregation, transformation on the data we've already downloaded, and then convert that into a smaller pandas data frame that we want to do our work on. So this way, we're caching the data at multiple spots. So database does some caching, the REST API does caching, and then our actual script grabs a large chunk of data so that we don't need to go for every single one of these tens of thousands of reports doing additional database queries. The second part is that we do this iterative analysis to reduce the workload. So the way I actually do things in practice is that I have a MongoDB, which has some description of our state. So for every analysis, what I do is I grab the previous state, so the report from the previous day or the last time it was available. I have this new chunk of data, and then the analysis code takes state, data, and generates a new state, which I can put back into MongoDB. So I'm only ever having to work with a single day of data at a time, and I don't have to do historical queries. So this puts a little bit of a constraint on what sort of analyses I can do, because usually I still want to have some influence from the past, but I need to write my analysis algorithm so they can at least operate only on a single chunk of data at a time. And a lot of these components we've made quite generic, so we can easily write new reports. So like in this case, I'm writing an analysis on some performance measure of how well we're able to match up our data. And I can just write a little adapter because I didn't actually have the column in quite the right format I wanted. So I can write a simple little line that will map one pandas series to the new one I need. And then I have several prepackaged analyses I use for multiple things. So for example, the success rate analysis I showed you earlier, I can now just write that I want to do this on a particular column of my data. So it's very easy for me to add new reports, and it automatically figures out how to do everything else. So in the end, these reports get stored as JSON documents in Mongo. And one thing that we found quite useful is that we can actually type these things with a library called Marshmallow, which is nice because you can then nest the documents, you can extend them. And in this case, all I do is I put some information about how I selected the data for the report, whether or not I consider it to be having an alert, and then the actual numbers I want to report. And if I need to keep some state about what I'm doing, I have the internal state there. And these Marshmallow documents are really easy to write. You just write basically a new class, which derives from schema. And then you say, it's like writing a SQL alchemy model if you're familiar with that. So you just write your fields, and then you write some typed way. And so it'll take care of dealing with all the non-JSON encodable things in your Python structure. Now, we still have a lot of jobs we want to run. So we are building an in-house cluster at Optiver. And what we're running is Apache Mesos. So if you're not familiar, this is a resource management tool which abstracts away resources using Unix C groups. And so you have 3 nodes that are masters that take care of figuring out where your task should go and run. And then the slave nodes run the task and report back. So if your jobs fail, it'll automatically take care of restarting them. And we're still in the process of building it, but we've already got quite a large chunk of resources. So this is the most recent one I grabbed. So we have now around 800 cores on our cluster, and 520 gigabytes of memory and 20 terabytes of local disk plus additional storage on the network. To manage our jobs then, we use another framework from Apache, Aurora. So Aurora is a framework for Mesos, so it takes care of telling Mesos what to do. And we found Aurora was quite nice because we can do both cron jobs and also one-time ad hoc jobs. So you write a little Python script that tells it what commands to run, and then it takes care of putting it onto Mesos and running it regularly. So then what we do to actually parallelize the runs is that we start with a lot of reports we want to run, and I split them at some high-level aggregation. So in practice, the way I make these report filters is I have a series of ways in which people want to drill down into the data. So I take the top-level filters for my data. So in this case, it's our trading environment and a market. And that becomes a job for Aurora or a Mesos task. And then within that, I do parallelization with multiprocessing in Python using joblib. So I download the data once for this high-level filter. So that's this first layer of caching. And then for each report filter, you grab the data you need, and you send the report filter the smaller chunk of data to individual core for joblib for processing. And then they all send the data back to MongoDB. So this works quite well. And again, there's a lot of jobs. So one of the problems we found in practice is you have to figure out, did everything work okay? How is my performance going? So we have a lot of custom tools in Optiver we built for monitoring production jobs. So one thing we have is an API which lets you pump basically any performance metric you want to a time series database on the back end. And we're running Grafana as a way of visualizing this data. So for example, we have this tool built by one of the operational people on our team to look at how the cluster is being used over time. So this is an earlier case in which we were running it, and you can see in the middle of the graphs is when my reporting jobs kick off. So there's a big spike in the CPU usage, and the number here is an average, so it's actually higher during the runs. So I think I hit something like 200 cores right now, or 400 cores on my jobs. And there's also a spike in the RAM and the disk usage, of course, too. But it quickly goes back over time. So my code is working fine. I'm not actually an operational person, so it's always good to check these things. We also have tools for monitoring, did our jobs actually, what's happening with all of our work. So we have what we call a health system, where we can basically pump a state. Is it running? Is it failing? Is there something wrong going on? Status messages, and there's a web API on the back end, which then you can then go look and see what's going on with all my stuff. So I can very quickly go to the website, and at the time I took the screenshot, I see, oh, one of my reports is currently in the middle of running. And again, we monitor our log files for errors that happen. So if there's something in this thousands of jobs that are happening, we can detect errors and respond to them, and we can track the performance of these jobs over time. So to recap the technical side of things, from a software architecture point of view, we use multiple levels of caching to try to reduce our impact on our database backend. We implement these analyses in an iterative way so that we don't need to actually look so far back in the past. And we use these JSON schemas in Mongo to allow us to evolve how our models and data structures look over time. Then we parallelize the data on our in-house cluster in multiple levels of parallelization. And we also monitor these using lots of different production tools to make sure that things are running the way we expect. So in the end, what we get out of this is a tool we use called the data dashboard, which again is a Flask REST API serving these pre-calculated reports from MongoDB. And then it's an internal website built using React, so the JavaScript frameworks, React, Redux, and HighCharts. And just to show you a couple of graphs from this, these are, again, real cases from the analysis. So on the left is a case for this success rate analysis. On the right is a case for tracking a quantile of the data. And so you can see the red highlighted points are outliers that the program detected, which also happen in this case to be downtrends. So it's a down arrow with a red highlight. And again, they're shading because I have actual measures of how uncertain I am about these numbers. So people, which I find in practice is quite important, because otherwise a lot of times people care a lot about these numbers and they might get overly excited about small bumps on this curve. So we're automatically detecting these trends and outliers and revealing them to users. We're clearly indicating the uncertainty, and this is something we run live in production every day with data coming in. So I have a slide here with all the different components we're using for different parts of our technology stack. I don't know, how am I doing on time?
You're doing good.
Okay. So yeah, I mentioned quite a bit of this, but I'm just going to emphasize some of the stuff. So on the cluster side, we're using the Apache framework, Mesos, and Aurora, and Python joblib, which I love for managing multiprocessing. I also learned earlier about this, more about async I/O in Python, so I think I'm going to go back and try to use this with some of my things now. For the database side of things, we're using Marshmallow for defining our schemas, MongoDB for storing these documents, and we do all of our REST API stuff using the request package and Flask servers and UWSGI for making our servers. Of course, we use all the SciPy stack, so Pandas and NumPy, SciPy. We use a lot of, we find Arrow is really nice for us because we work a lot with this operational data and things in different time zones. So it's a library which lets you convert date times easily to different formats in a really expressive way. Another thing we've also started using recently is this library PyDash, which lets you write some functional programming type styles with your data in Python. For the analysis side of things, right now, most of the work is basically just actually taking equations or algorithms from papers and writing them in SciPy, NumPy, Theano in some cases. I play a little bit with actually Monte Carlo algorithms as well, PyMC3, which many of you are familiar with. But right now, for this sort of thing in practice, it's not really fast enough to run for these sort of large jobs, I find. So it's nice for doing some exploratory things, but I'm not using so much for our live data. And then, on our dashboard side, we're using the React framework with Redux and high charts for visualization. So with that, I'll emphasize that we're always hiring. So if you're interested in these sort of data problems and working with, kind of different data problems in some other places, we're hiring researchers, data scientists, data engineers, DevOps, and traders as well. So thank you guys for listening, and I'll be happy to take any questions.